So, more stuff from eBay. This is a medical grade isolation transformer. Picked it up for a really good price. Basically so that I can probe on the hot side of the power meter project and whatever with my oscilloscope without having issues with shorting shit out and possibly blowing out the input to my oscilloscope or popping fuses or melting probes or whatever when they ground it accidentally. Not that it stopped me from trying to hook this up. As you can see, here's my wonderfully safe line connection. One of the people I learned electronics from generally called, basically, we often had, like for testing amplifiers and so forth, generally the way to hook them up was literally a line plug on one end, alligator clips on the other. So this is just stripped wire. And the colloquial term for that particular setup was a suicide cord, which I found very kind of amusing. So this is hilarious. It was $60 plus like $17 shipping, and this weighs like 35 pounds. Like heavy package, and it's big. So I think I wound up getting a good deal just because it's I bet it cost a lot more to ship than they thought it would. Anyways, let's have a look. As you can see, the box is kind of falling apart, presumably mostly because it's just really heavy. And there's not much packaging in here. So, that knob. So, there it is. You can see that there's very flimsy folded tissue paper. Here's an invoice, and so this was at one point a inflatable air pouch for padding. That didn't make it very far. So let's. That is heavy. So, on the face of it, not much to look at. We have a metal box. And there, one of my light bulbs. That's it. Here. So, metal box, outlets. Thing of interest. This green dot here, that means these are hospital grade outlets. They're Hubble branded, actually. Got a big power switch. And then on the other side, PPS isolation transformer, sensor medics, big IEC inlet with, and then that's it. So let's pull the cover off, and you can see that we have screws here, and then it looks like this is a wrapped sheet metal thing that'll just kind of lift out. Nicely made. So I wonder if this is just a transformer or if there's anything else in here. So the way this works is I'm probably going to plug this outlet strip into the isolation transformer, and that way just anything on my bench will be isolated. Apparently I'm supposed to refer servicing to qualified personnel. I don't know if I'm qualified, I certainly talk a lot. Another thing I've noticed is that this is very, I don't know if it's steel. Magnet got to, but it's definitely like 2mm sheath. It is not all the screws. Oh boy, there's something loose inside of that. So you can see, A, it's been dropped. Probably not a big deal. And B, there's the footprint of the actual transformer. There's probably more stuff I should probably disinfect, but I'm not going to. So this is sold for, basically isolating, equipment, in a hospital so that to prevent, protect people from shocks. I think a fair amount of stuff, like hospital grade electronics just come with an isolation transformer as a safety measure. But I'm honestly not sure. So 8 screws. we are. And here is what was loose, which seems to be a lock washer. So, there is not much in here, aside from one hell of a couple terminal blocks. So, really big chunky transformer. This is supposed to be rated at 8 amps. You can see over here 115 volts, 50 to 60 hertz, 8 amps. A lot of power. So you can see here's your power input. So that's interesting. So you can see that it appears that right here, these two right here are the outputs. Because you can see that they're zip tied together, but they go up here to this terminal block, and then through this terminal block into the outlets. So the other thing you can see is that these two windings are strapped and these two windings are strapped. So it looks like I can probably use this as a 120 to 240 volt step-up transformer as well. Because if you see the way these are strapped, you know, basically you have two output windings, gray and green, and then they're strapping the gray, or it's gray and blue, and they're strapping the blue-white and the gray-white in parallel, or together, and the blue and the gray in parallel, or together. I said the same thing twice. And then they're taking, basically they're going off of there. It's also interesting that look at how heavy the cables are here, and then the cables actually going to the outlet are just these little, feels like 18 gauge. But I bet if I moved this shorting shunt to the center, I bet we'd get 240 out here. You can also see that the power comes in, goes over to here, and it looks like there is a LED in here. You can see the little diagram, which is what I bet these two connections here are for. And then you've got, you know, basically, so it looks like they've, you know, just hard soldered the LED connections to the outlet. So this is probably also a circuit breaker, I would guess. So that's another thing of interest, as you can see that they've got really, really badass ground strapping. One of these, this is coming from the input, and then this is going to the, yeah, so this is the ground strapping coming in from the power input, you know, the IEC connector. This is going to the outlet plugs. And then this is actually just a strap that straps this section of the housing to this, which is kind of wild. I guess that they didn't really trust the screws, so they added an entire, you know, a purpose-specific ground strap just to strap the various casing sections together. You know, in other words, that they want to be absolutely, completely certain that this could never be hot. Which is nice. It's very high quality. So, let me just undo this nut. There it goes. Another thing I'm noticing is that everything in here has shake-proof washers on it. You see here we have, this isn't actually, it's got a little spring washer on there, which is, you know, an anti-shake thing. We've got this, and then there's a you know, many-tined washer on there, and that's actually probably to ensure, because I think this is aluminium, so that's probably to ensure that this breaks through the oxide layer when they clamp the crap out of it. So what interests me is all of these primary windings. So here's your power inlet, so your power comes in here, goes to the switch, and this is indeed a circuit breaker. Amps 8, max volt 250, hertz 5060, delay 655, that's probably 655 nanoseconds. And then it's got a light in it, lit test 100 kilo ohm. Toggle T amps is 10. If I can't get that in focus. This also looks like it's fairly old. There's that little label. So judging from, you know, and it's also UL rated, because everything in here is going to be rated out the orifice of choice. So look at all of these primary windings. First of all, you can see this is made in the US of A. That's nice of them, Bristol Lake, Wisconsin. blah blah blah, S71, 181, blah 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 blah, ref B. You can see these great big screws holding it together. Again, there's, you know, anti-shake washers on there. Anti-shake washers on this side. I don't know where that washer that was floating around the case came from, because you can see that these, it's the right size to have been one of the ones that was on one of these screws, but it they all have them on it. So that's slightly worrisome. You know, I've got there's been a piece of metal rattling around the case for who knows how long. Kind of bizarre. So you can see the primaries here, secondaries on the other side. One of the things I want to do is I want to measure the primary to secondary capacitance. So then you can also see this really interesting. So here's your power input, and you can see it's going to here, here, and then so hot and neutral. I'm not too sure which is which. I don't remember the color code. But look at all of these taps. I bet this transformer is also used like in an active line filter setup, where basically they switch around in the taps. So actually one thing that would be interesting would be to measure the voltages at a lot of these points when the system is on, which I think I will actually do. Because basically when it's on, it's going to be acting, you know, just looking at the voltage between these points, these are going to be acting just like an auto transformer. So, use my 113, which turns out to be a very nice meter if you keep its limitations in mind. Let's see. It's got a nice, rather subdued green LED in there. So it's recent enough that the indicator light isn't a neon, because you can see that it's a green LED. So that should tell you something about the date. Yeah. Let's actually, let's go. 116.2, so that's our secondary. So $96, 106, 115, 125. Okay, so that's interesting. Look at that. So I bet this is to let them use this in Japan. Because you've got, or in areas with low line voltage. So if your line voltages are, you know, 85, you use these two. Oh. So if your line voltage is really low, you can just hook up here and still get, you know, 86. Here's 96, 105. So you could use these two, you know, these two taps here, you know, with your primary to give you 120 volts output. So it looks like you probably could use this for line stabilization if you wanted to. So that's just conductive, which is what it's telling me. So, you know, this should be the same thing. 85, 86, 96, 106, 113, 25, yeah. So this looks just like what they do in like the line stabilizers, where they switch between the various taps on the transformer to maintain a fairly constant output voltage. It's fairly common, and I bet they can also tie the two windings in series. That's actually an interesting idea. So let's turn the power off, kick over to ohms. So 0.3, 0.4, still really low. Yeah, this meter doesn't go low enough. I need a much more precise, like, milliohm meter. Actually, I think the keith lead can do that. Let's see what this. I don't remember how precise the keith lead meter goes. Oops. Yeah, that gets me down to milliohms. So you can see here's the first tap. 0.0013. Actually, here's the so there's my test leads just shorted out. And what's like the resistance between these 2 points? Okay, yeah, I think I'm basically out of the working range of my meter. Or this isn't wired the way I think it is. Could be either. I've got to be in low ohms range. Basically, I need a milliohm meter, which I don't have, or something that does Kelvin connection. So what can I say? Or the transformers being relevant. I don't know how. But that's quite intriguing. So, you know, just typical interesting stuff. So one thing I can actually look at that would be interesting would be to try and see if this will get down far enough that I can measure the capacitance. So let's go over to, and this goes down to nanofarads. So 0 nanofarads. So it's just measuring 1 nanofarad. This is not precise enough. Let me see the, I have a couple meters I can try, but I don't know if, I mean, really you want very, very little primary to secondary coupling capacitance because that's going to determine how well this thing rejects common mode garbage. So, so that is, so you can see that as I kind of move the leads around. So let me just kind of, actually I know why it was acting up. It's because no, that wouldn't be it. Unplug it and turn it on to try and get all this switching stuff out. So, man, I'm just down in the garbage. So there it is touching. And there it is not touching. So it looks like it's probably in the range of a couple hundred picofarads, which is decent. You know, again, this is going to be a function of the winding topology, how they wound it. You know, hopefully there's a decent separation. This should very much not be bifilar wound. Actually, there's an interesting question. What is the capacitance to ground? Okay, so there's a lot of capacitance between the ground and the output. I'd make a connection. There's a fair amount of connection there. So it looks like, I don't know how much of this coupling is between the windings and ground and then through the ground to the other area. It'd be interesting. I wish there was some way I could take the ground out as a capacitance path and just test the interwinding capacitance rather than the capacitance to ground, because any capacitance to ground should be mostly irrelevant because that should just shunt away any garbage. But basically the issue is if you're grounded and you touch the output and the output has a capacitive path back to the input, you can have some current flow through ground and then give you, you know, that'll give you, you know, if it's isolated, it won't really hurt you, but it's a tingling sensation, which is, you know, not exactly desirable. Other stuff is like, I don't know how much I trust these windings or these wires for 8 amps. You know, I mean, it seems like the wires in the transformer are very large and the rest of them aren't. But the thing that concerns me the most is just where did this come from? Anyways, there's a fun little medical grade isolation transformer. So what makes it medical grade? Well, ratings and then the fact that these are really sticky. I mean, the plugs are very stiff. You have to really push to get the sockets in there. Some other stuff, like I don't know what these are. Actually, I bet I know where that, you know, it looks like there was something that went here. You have those 2 screw holes. I don't see anything on the inside, but I bet that there was like something that sat into these slots and like latched downwards that maybe, you know, covered the plugs, and that might have been where some of the stuff came from. Or this could have fallen in through there, but that seems kind of unlikely. You know, because this this washer can just squeak through one of these slots. Maybe somebody thought that was a cute way to store it. If somebody did, he's a dumbass. But, yeah, actually, so cool. So there's a little rather enormous medical grade isolation transformer. So this is just continuing on kind of the ongoing saga of why an isolation transformer is useful for testing purposes. So what we have here is, this is the isolation transformer, and then this is just what's colloquially known as a bad idea, which is a power cord with stripped ends. These were, kind of jokingly called a suicide cord at one of the places. A suicide cord at one of the places I worked at. Often you'd have something that goes from a plug to 2 alligator clips, which is really useful in situations where you're trying to power up a piece of equipment and there's cord issues or whatever. When you want to test a transformer, you can do it on a bench like that. Here I have a rather low quality AC voltage detector. So if we just plug this in right now, we can see that black is hot, there's nothing on white, and there's nothing on green, which means I can touch either of these without any trouble, but I'd get a nice tingle if I touched that. Rather annoying voltage detector. So what I can do is if I plug this into the isolation transformer, interestingly enough, what now happens is it's not hot. So what's actually going on right now, one second. So what happens here is basically a line detector like this. What it does is it actually uses capacitive coupling to you as well, and what it does is it detects, basically the changing field of the line. But this isn't a particularly sensitive one, so it needs, a fairly large slew rate, or a fairly large slew, about 100 volts. A few hundred volts. So actually, with 120 volts, you have your 0 volts, and it actually swings up to 160 and down to 160. So this is, approximately 169 volts positive and then 169 negative. So if you rectify this properly, you can actually get twice the voltage. But the overall average voltage is RMS 120. So you can actually see that your peak-to-peak voltage here is going to be 2x 169. Anyways, what's happening is, so, with your line voltage, you have, your neutral, which actually runs back to your junction box. So your neutral actually runs back to your junction box and is typically earthed at the circuit breaker box in your house, at least in America. I don't know, other country electrical codes very well. So this is your neutral. And then you have your line, which is your line. So this is the voltage that's doing that. And this runs off to the power pole. So in this situation, what goes on is that, again, you've got a lot of voltage change here, 300 volts plus peak to peak. And the neutral is totally, nothing's going on. Which is why when you put this near a neutral, nothing happens. When you put it near the line, it detects it. So then we're going into a transformer. Probably didn't get the turns ratio quite right. So we go into this transformer, and then what happens is, we have the second earth connection, which actually also is earth at the junction box, but then runs past this, and so then here's your your outlets. I'm probably not going to get the slot sizes correct, but one of these terminals runs to there. I may have the phasing backwards. But what you can see is that basically neither of these are referenced to the the neutral or the earth. So what happens is that because there's a small amount of leakage here, and most of it's probably leaking to ground, because again you've got ground in close proximity. They're inside the transformer. They're bundled together. Is that what you instead wind up with is 2 waveforms that are 180 degrees out of phase. If we ignore my horrible art skills. So, let's call this 1 and let's call this 2. So this is 1 and this is 2. So what happens is your peak-to-peak voltage here is, basically 1/2, the peak-to-peak of the input, because your overall voltage, if you ground, 2, you get, it's a differential voltage, basically. And I'm not explaining this very well because I'm, whatever. Anyways. So the end result is that your peak-to-peak voltage is much smaller. It's your peak-to-peak is actually going to be 169 volts because it's half of the normal peak-to-peak voltage. But the overall RMS voltage is the same because, again, the RMS is measured between the 2 taps. And that's just not enough to set off the voltage detector. But what we can do, if we're feeling rather unsafe, though actually, assuming the transformer is working properly, it should have no negative effects, is we can take the output of the transformer. So if we go in here and this transformer is currently off, it's got, you can see the on and off. And what we should be able to do safely is ground either one. So again, remember, because these are both floating with reference to the ground, we can optionally tie the ground to either this winding or to this winding. So we can basically say we want this winding to be our earth referenced, and then this winding will swing up and down and relative to that one, or vice versa. So what we'll do here is we'll say let's ground the traditionally hot. Comes up without any problem. And you can see now there's nothing there, but the hot is triggering basically my voltage detector. And if I get that on clip there, and then I can just go over here, and now the neutral is safe and the hot is hot. So what this means is that, say if I'm trying to, if I have a circuit connected, so what happens is, say I have this, my device under test plugged into this outlet. I come in with my oscilloscope probe, and if you remember correctly, the ground on the oscilloscope is referenced to earth ground. What I can do is that, assuming I don't have any of these connections here, if I clip onto, say, the hot, I clip onto winding 2 right here, what suddenly happens is that the hot is now referenced to earth ground and the neutral is what's moving. But it means that I can clip onto the hot and I won't have any, there won't be any current flow aside from whatever capacitively couples across the transformer, which is very small. And then if I want to measure the other voltage, if I want to do measurements here, I just make sure I've ungrounded 2, clip onto 1, and now I'm earth referencing, basically what's generally the neutral. And this is, this doesn't seem like that big of a deal, but then you realize that you have something like this. This is my little test setup for the power meter project I'm working on. And as you can see here, basically this is 120 volts AC, and it comes in, and I may need to be, sticking my scope on, here's the series resistor, this is a 0.05 ohm resistor. I may need to be, able to stick my oscilloscope, right across that resistor to make sure that I'm actually getting valid current measurements. So the only way you can do that is if you can basically break any reference to, basically the neutral that's coming in through your power, your outlets. Because all of your, all the outlets in your house share this reference, basically the neutral is referenced back to ground, typically at your breaker box, and then the line is, lots of voltage. So what would happen is you can see that if I were to take my oscilloscope probe and then say, oh, I want to measure, try and clip onto the line here to say measure, let's say I have a series resistor here, and I want to measure the current there. If I clip this onto here, what's going to happen is that basically I'm shorting through my scope probe the line I'm shorting that voltage to ground through the scope. So that's probably going to blow a breaker. It may blow up damage the scope because suddenly you've got 15 amps flowing through here, or whatever your breaker things are for a second or two. Or the other problem is that there is resistance in your neutral. Again, you've got these long wires, maybe 30, 50, 100 feet running back to your breaker, which is going to be basically a whole lot of little resistors. Basically one long resistor. It's going to be small, but it's very common to, if you measure your, you measure your voltage between your hot and your neutral and your ground to have, 1 to 4 volts here. Well, in my house it's about 3, which is, indicative of not the highest quality, but what do you expect from a house made in the 60s? So what happens is then, if you go like this, and again you do this, you clip onto there, you're grounding this, you're going to have whatever that current is flowing is going to be shared across your scope. It's probably going to be an amp or two at least, and if you have any RCDs, GFCIs, ground fault circuit interrupters, it's going to trip all your residual current detectors because suddenly you've got a whole bunch of current that should normally be returning through the neutral, returning through, basically returning through the scope earth. So for any sort of situation where you want to do measurements, that are referenced to, the input without having without having a power transformer in the device, you have to have an isolation transformer. And the other thing that's relevant in this is that this makes, if it's less relevant with 120 volts because you can't really kill yourself with 120 volts without, a little bit of effort. But what this also means is that, if you're working on a circuit that's powered by 120 volts, and you're earthed and you touch one of these two terminals, there won't be very much current flow because again, there's no path for the current to return, and flow through you. Of course, if you make contact across them, say grab this one with this hand, this one with this hand, you will get the current through your chest and that'll hurt you. But it's, a lot better than, say you're touching something grounded or you're standing on, something grounded, which is not that big of a problem most of the times, but it's, like if you're in a puddle. Just don't do electronics in a puddle, I think, is the general consensus. But what will happen then is that, you only need one point of contact because the other point of contact is through your body. And, it'll shock the crap out of you. But yeah, so, so this is kind of is I have to put this on the isolation transformer so that I can actually stick my scope in here and say clip onto these points and actually look at them. So if you don't have an isolation transformer, there's no way to really do any sort of verification on this side, which actually wound up, I wound up doing that mostly because I somehow read 9600 or 600 baud as 9600 baud, but that's another story of me being derpy. But again, any measurements in this section of the circuit at all have to be done on the isolation transformer. Well, they don't really have to. You can be clever if you know things and you can float your scope and other stuff like that. But it's never, there's a lot of more safety concerns and you have to be much more careful in that sort of situation. So, in other words, if you don't know what you're doing, don't do it. But anyways, so, there's kind of just a quick overview of why the isolation transformers are, very useful and they will help keep you safer, particularly if you're working on things that are line connected. And they'll let you work on things that are line connected if you need to do any sort of measurements. So the other alternative to an isolation transformer is something called a differential, an isolated differential scope probe, which are nice to have, but they're really expensive and they typically need batteries. We have a couple at the lab where I work, but basically what it is it's, it's basically kind of just well, I don't think I can really draw it, but it's generally like a circuit, a differential amplifier. So and then it goes through, they typically apply some modulators, and then it goes through, say, a small transformer, however they want to do this, and then there's and then, so here's your two inputs, and then what typically happens is, basically you'll have, a battery over here, and then you also have batteries over here. So like the ones I have at work take 6 AAA or 6 AA's, and they chew through batteries like a motherfucker. So the idea is basically you have a situation where you have these two inputs which are completely floating, and then there's, some sort of mechanism, a transformer or some sort of other, isolation barrier, and then this whole section can be floating at 120 volts or whatever. You can reference it to whatever the hell. You have, low coupling across the transformer, and then this goes into your scope and it's galvanically isolated, but they're passing the analog voltage across the isolation barrier somehow. They could use transformers, they could use capacitors. There's, you can actually buy off-the-shelf isolation. You can buy like a little 16-pin dip with a whole bunch of missing pins that is like a closed-loop feedback isolation amplifier. With the bandwidth is limited, but it's available, and they're also expensive, for like $15 for a part. But, in other words, you either have to have a technique like this, or you have to have, an isolation transformer. The advantage of a dedicated purpose, isolated differential probe like this is that you can be probing two different sections of the circuit at two different voltages simultaneously. Whereas with something like this, you can obviously see that if you try, if you want to be probing line 2, so you connect your probe up here, and then you're like, oh, I got to look at the line 1 too, and then you connect another probe over here. It'll short through this, it'll basically short out through the 2 ground leads, but that's pretty simple, and I would hope most people wouldn't think about doing something like that, because obviously if you're connecting your grounds to both terminals, something's going to go wrong. You can also fake, you can do also with differential. You can also use 2 probes as a differential probe with, in-scope math if you're feeling fancy. But that's never quite as good because, if you have a small signal vintage on a large carrier signal, you'll probably be swamped in noise because your most scopes are only 8 bits. So anyways, so that's why, something, an isolation transformer is such a useful tool in this sort of situation.